Here's a problem that looks impossible. You have a sequence of observations, and you want the single most likely chain of hidden states behind them. The catch is that the number of possible chains explodes. For n states over t steps, that's n to the power of t paths, which is hopeless for any real sequence. Andrew Viterbi solved this in 1967 with one elegant idea, and today that algorithm quietly decodes your speech, your text, and your wireless signal. Let's see how it works. Walk through the algorithm one step at a time because the whole trick lives in what it keeps and what it throws away. You move through the sequence step by step, one observation at a time. At each position you consider every possible hidden state that could have produced what you just saw, and you carry forward the running probability of arriving at each of them. Now the key move. For every state at this step, you keep only the single best path that reaches it, along with a backpointer noting exactly where that path came from. All the weaker paths into that state get discarded, because if a path into a state is already losing, extending it further can never make it win. When you reach the end of the sequence, you look across all the final states and pick the one with the highest probability. That single winning state is the tail end of the most likely hidden chain through the entire sequence you just processed. Then you follow the backpointers in reverse, hopping from each state to the one it came from all the way back to the start. That walk reconstructs the whole optimal sequence of hidden states, and you're done, no enumeration required. This is the classic decoder for a hidden Markov model, the piece that answers the question, given what I observed, what hidden states most likely produced it. So here's why this matters so much in one comparison. Brute force says try every possible state sequence, score each one, and keep the best. That's honest, but the count of sequences grows exponentially with length, so even a modest sentence would take longer than the age of the universe to decode. Completely unusable in practice. Viterbi keeps only the best path into each state at each step, and that one restriction collapses the whole search. The work now grows linearly with the length of the sequence, turning an impossible exponential problem into a fast, practical computation you can run in real time. The insight is simple but powerful. The best path to a state can only be built from the best paths that led into it. Let's lock in the three ideas that make Viterbi tick. It's dynamic programming at heart. The best path to a state at time t depends only on the best paths to states at time t-1, so you build the answer up incrementally and never redo work you've already done. Backpointers are what let you recover the actual answer. Scores alone tell you how good the best path is, but the trail of backpointers is what lets you walk back and read out the full sequence of states. And the payoff is turning exponential search into linear decoding. That's why Viterbi shows up everywhere hidden states get decoded, from speech recognition and part of speech tagging to bioinformatics and the error-correcting codes in your wireless connection. In fact, decoding those convolutional codes was its very first use, before it ever touched language at all. Alright, for takeaways worth keeping. The Viterbi algorithm finds the single most likely sequence of hidden states behind a sequence of observations. Its insight is that the best path into any state depends only on the best paths one step earlier, so it builds up incrementally. At each step it keeps just the best path per state plus a backpointer, then traces those pointers back to recover the whole chain. That turns an exponential search into a fast linear decode, powering speech, tagging, and error correction. If the classic algorithms behind modern AI intrigue you, Standarity.com is where these breakdowns live.